Welcome to this new video on period caping and base shear correction. So in this video we shall be understanding what is meant by period caping and what is base shear correction, how to apply it, what is the implication on the structure after applying the base shear correction. The meaning of period caping is that the code imposes a restriction on the upper limit of the time period of the buildings, so that the natural time period of the building is not very large, that is, the building is not very flexible. So we are using the symbols capital T for natural time period of the building in the first mode, T suffix A, the approximate time period of building as prescribed in code. So the intention of the code is this, that the T is less than TA. That is, my building is not very flexible. So let us see the period caping formulae available in other international codes. So let us first start with Indian code. So Indian code has divided buildings in different categories like bare frame buildings. Bare frame building means there is no infill. Brick masonry infills are not there. So in this category you have the RC moment resisting frame, and then composite moment resisting frame and steel moment resisting frame. For all these, period caping formulae are given in terms of the height of the building. For shear wall building, a more lengthy formula is given, where AW is the area of the shear wall to be computed by a formula given in the code, and H is the height of the building, and D is the dimension of the building along a particular direction. For all other building for Indian code, the approximate time period formula is given by 0.09 H divided by under root D. H is the total height of the building, and D is the dimension along the direction in which the earthquake is acting. Since in the plan we have the two major directions of the building, the shorter direction and the longer direction, so we shall have two time periods, approximate time periods given by this formula, one along the short direction, another along the long direction. In uniform building code, the formula is simple, a coefficient and height to the power 0.75. The coefficient is 0.03 for RC frames and 0.02 for other buildings. SC 716 gives for RC moment frame TA equal to a coefficient into height to the power 0.9, for steel moment frame another coefficient and height to the power 0.8, and eccentrically braced steel frame it is 0.000731 h to the power 0.75. H is the height of the building. In this slide, small h and capital H are synonymous. For Eurocode, the formula is also simple, CT h to the power 0.75, CT equal to 0.075 for RC frames and 0.085 for steel buildings. New Zealand code gives the period formula by a dynamical equation which involves the weight of the floor and the displacement, lateral displacement of the floors UI. Now, how does the code ensure that period caping is applied? So for that, let us understand a little background in the dynamics. So here omega and F are shown. Both are frequencies. Omega is the angular frequency of vibration, and F is the cyclic frequency of vibration, that is per second how many cycles are taking place. Now T is the time period, so we have the very simple relationship F equal to 1 by T, and both omega and F are proportional because they are multiplied by twice by F. So time period is only reciprocal to the frequency, so if one increases, other will decrease. So with that, larger the frequency, we have smaller time period by this expression, and this indicates a stiffer building. Similarly, smaller the frequency, larger the time period, and this indicate more flexible building. So code wants that our dynamically computed time period, which is the inherent dynamic property of the building, should be less than or equal to the approximate time period value. So what does the code says? Since the time period indicates the flexibility or stiffness of the building, the code is indicating that the building should not be very flexible. You have to note one thing here, the code does not specifically mention about the time period comparison, but it compares the base shear with respect to this time period and this time period. Both indicate the same thing, as we'll see gradually in coming slides. So you have suppose the approximate time period formula value is this much length, so a certain value, and the dynamically computed time period, which is the real time period of the structure out of dynamic properties, is longer than this. So code says this should not be longer. So what we do, we have to reduce it. So we can reduce it up to here. How we can reduce? One thing, simple thing is, of course, you can increase the sizes of the members, and the system will become stiffer and time period will reduce. So this you can do. However, the code is not telling you to increase the size of the members directly, but it is implying something indirectly, as we will see in the coming slides. Code wishes that the building is not very flexible, that we have already mentioned. This is achieved through what is known as base shear correction. Very important thing for any building design or even also in other structural design. So let us understand what is base shear correction, how it is applied, what is the implication. So symbols that we are using here are VB, base shear computed using the dynamic time period T, and BB bar is the base shear computed using the approximate time period TA given in the code. So codal prescription is this: BB should be not greater than BB bar. If it is more, if BB is less than BB bar, BB should be greater than or equal to BB bar, but if it is less than that, as per this condition, then apply base shear correction. So we'll see that this BB and BB bar are connected to T and TA, so indirectly it is comparing actually the time periods. This is very clear here in the design spectrum. So we have drawn some schematic design spectrum, say of Indian code or any other code. So you have to apply base shear correction because your dynamically computed time period T is more than the approximate time period given in the code, caping period given in the code. This is the SA by G axis. So since T is larger, you have the SA by G at T at this point, which is smaller than SA by G value for TA corresponding to the TA time period as given by this point. So this is the condition inherently in this with respect to the design spectrum where you require the base shear correction. Now if you look at the base shear values given by the code, say Indian code, then it is BB equal to Z by 2 I by R, SA by G into W. So SA by G, you have two values here, one with respect to SA by G TA and another SA by G T. So if we apply these two separately, we get two base shear values. So when you are using the dynamically computed time period T, you get the base shear, which is BB, and when you use the approximate time period of the code, you get the base shear, which is given by BB bar. So base shear correction is nothing but applying multiplying all the response quantities by a ratio of BB bar by BB. So this is the factor through which you have to multiply all the response quantities. What are the response quantities? Response quantities are all the internal actions which are arising out of the external actions. So these are bending moment, shear force, torsional moment, and so on. So all these quantities that are computed out, of course in a software it will be given by the software, have to be now multiplied by this factor BB bar by BB. And as you look here with respect to the SA by G TA and SA by G T, BB bar is here higher, and that is why base shear correction has been implied, and so this ratio BB bar by BB is always greater than 1. So your response quantities will be enhanced or increased in the design. So with this understanding, let us make the concluding remarks for this video. Approximate codal time periods are called period caping values. Base shear correction to be applied when BB bar is greater than BB, which indirectly implies T is greater than TA. Base shear correction factor is BB bar by BB. With this correction factor, you have to increase all the response quantities. In design software like SAP 2000, you can increase the scale factor in the seismic action by the ratio of BB bar by BB, and this will enhance all the response quantities multiplied by this factor. Base shear correction may not always ensure that T is less than TA physically, because by increasing all the actions by that ratio BB bar by BB, you are increasing bending moment, shear force, etc., which in design may not require increase of the size of the section. If they are safe only by increasing the steel, then you need not increase the size, and in that way it will not change the stiffness of the building. However, you have increased the strength of the sections, and we shall see in future videos that strength and stiffness are related. So in some indirect way, you are ensuring this T by less than TA condition in the system. Thank you very much for watching the video. Please subscribe the video, like it, comment it. You can put all your queries in the comment box. I shall be glad to answer all this. See you again in the next video.